Hello everyone, my name is Dr. Raj Dandekar. I graduated with a PhD in machine learning from MIT in 2022, and I am the creator of the Build DeepSeek from Scratch series. Before we get started, I want to introduce all of you to our sponsor and our partner for this series, invideoAI. All of you know how much we value foundational content, building AI models from the nuts and bolts. InVideo AI follows a very similar principle and philosophy to that of us. Let me show you how. So here's the website of InVideo AI. With a small engineering team, they have built an incredible product in which you can create high quality AI videos from just text prompts. So as you can see here, I've mentioned a text prompt, create a hyper realistic video commercial of a premium luxury watch and make it cinematic. With that, I click on generate a video. Within some time, I am presented with this incredible video, which is highly realistic. What fascinates me about this video is its attention to detail. Look at this. The quality and the texture is just incredible. And all of this has been created from a single text prompt. That's the power of NVIDIA's product. The backbone behind the awesome video which you just saw is NVIDIA AI's video creation pipeline, in which they are rethinking video generation and editing from the first principles. To experiment and tinker with foundational models, they have one of the largest clusters of H100s and H200s in India and are also experimenting with B200s. InVideo AI is the fastest growing AI startup in India, building for the world. And that's why I resonate with them so much. The good news is that they have multiple job openings at the moment. You can join their amazing team. I am posting more details in the description below. Hello, everyone, and welcome to this lecture in the Build DeepSeek from Scratch series. Today, we are going to proceed ahead in our journey of understanding the attention mechanism. And briefly speaking, here's our plan. Eventually, we know that we want to understand multi head latent attention, which is one of the key components of the DeepSeek architecture. But to do that, we need to proceed in a step by step manner. So initially we started out with understanding self-attention. We finished this in the previous lecture. So if you remember in the previous lecture, we saw exactly the step-by-step procedure of how the self-attention mechanism operated. We started with the query, key and value trainable weight matrices. We multiplied the input embedding matrix with these and got the query, key and the value vectors. Then we multiplied the query matrix with the keys transpose to get the attention scores. We then scaled the attention scores with the square root of keys dimension, applied softmax, and we got the attention weights. And finally, we multiplied the attention weights with the values matrix and we got the context vector matrix. The way to interpret the context vector matrix is that essentially every row of the context vector matrix corresponds to the context vector for that particular token. So if you see the input embedding matrix, every row corresponds to the input embedding vector for the next day is bright in this example. Similarly, in the context vector matrix, the first row corresponds to the context vector for the second row corresponds to the context vector for next, etc. So the whole aim of self-attention is to take the input embedding vector and convert it into a context vector. And why does it do that? Because the context vector is much more richer than the input embedding vector. The input embedding vector just contains information about the semantics of the word, but it does not contain any information about how that word is related to all the other words around it. On the other hand, the context vector contains information of not just the semantics, but it contains information of how much importance needs to be paid to all the other words or tokens surrounding it. And that's what makes the context vector much more richer in representation than the input embedding vector. So today what we are going to do is we are going to look at something which is called as causal attention. We have already looked at self attention, and the next step along our journey to ultimately understand multi head latent attention is causal attention. As the name suggests, causal implies that so one thing causes another, right? So we only need to look at those things which are responsible for producing the next token. And I'll clarify what this means. But causal attention is a central building block of understanding multi-head attention, and then eventually understanding key value cache, and then ultimately understanding multi-head latent attention. So let's begin our journey of understanding causal attention. Before we get started with the lecture, I want to just take a quick uh, I want to explain a quick summary of how exactly the next token prediction is done, so that I can explain or set the context for causal attention in a much better manner. So let's say we have the Harry Potter's first book, right? And that's a part of the data set which we are using to pre-train the large language model. And so for the sake of simplicity, let me just take a screenshot of the first page over here, and let me bring the screenshot onto my Miro board. So I have brought the screenshot of this first page over here. And now let me show you how the input and the target pairs are actually constructed to be fed to the transformer architecture. So here's how that's done. First, we determine something called as the context size. So if the context size is equal to 4, we create a sequence of 4 tokens. So this is my first input, and then I also determine something called as a stride, which means how much I have to skip before I create the next input. So this is my first input, this is my second input, this is my third input. So similarly, what I'll do is that I will divide the entire data set into chunks of 4 words or 4 tokens, right? And then based on my batch size, I will have a matrix which is created. So that's, let's see, the input batch 1. So if the batch size is equal to 6, or if the batch size is equal to 8, then the first batch will have, let's say, the token IDs corresponding to Mr. and Mrs. Dudley. That's the first row. So let's say this is 1, 15, 18, 22. The second row will be the token IDs corresponding to these 4 tokens. So that will be something like 3, 4, 5, 6. Similarly, I will have 8 rows like this because the batch size is equal to 8, right? And why do I have 4 columns? The reason I have 4 columns is because the context size is equal to 4. So that's how the input batch is created. So this is my first input batch. The way the output is created is that every input is essentially shifted to the right hand side by 1. So this is my first output, this is my second output, this is my third output, etc. So once you get the input batch, getting the output batch is very easy. You just shift the input to the right hand side by 1. So this will be something like 15, 18, 22, 3, etc. So that's my output batch 1. Now if you look at the first row here and the first row here, that's my first input output prediction pair. So for example, let's see, so the input will be Mr. and Mrs. Dursley. That's the input. So this corresponds to 1, 15, 18, and 22. And then the output is the input shifted to the right by 1. So then this will be and Mrs. Dursley off. That's the output. Now, if you see within this one pair of inputs and outputs, there are actually 4 prediction tasks. The first prediction task is when Mr. is the input and is the output. The second prediction task is when Mr. and is the input, Mrs. is the output. The third prediction task is when Mr. and Mrs. is the input, then Dursley is the output. And the fourth prediction task is when Mr. and Mrs. Dursley is the input, then off is the output. So if you see every row here, although it looks like we have 4 tokens, right? So there might be just one prediction task which is predicting the next token. But that's not the case. If the input is Mr. and Mrs. Dursley and the output is and Mrs. Dursley off, if the context size is 4, there are 4 input and target prediction tasks or input output prediction tasks which I've written over here right now. The thing which I want you to focus is that whenever you are you're predicting certain output. So for example, when Mrs is the output which is to be predicted, the input is Mr. and. When Dursley is the output which is to be predicted, the input is Mr. and Mrs. So let's take a look at the data set now, and let me clean this further to explain this point to you. So what I'm trying to say is that when Dursley is the output, let's say if Dursley is the output, the input is always the tokens which only come before Dursley. Similarly, you take any output, you take Mrs as the output. If Mrs is the output, the input is Mr. and. If you see, the input is Mr. and. So for every output, so wherever you go in this, so let's say if you go in this, you let's say if this is the input, and then the output is shifted to the right by one. Now within this, there are four input output prediction tasks, right? If you see was the output, you will see that Mrs. and Dursley was the input. If thin is the output, then was, Dursley, Mrs. is the input, etc. So based on the context size, whenever you have an output, the first conclusion from today's lecture is that the input is only the tokens which come before the output, right? So essentially what I mean to say is that uh, if you have the input as oops if you have the input as let's say Mr. and, if you have the input as Mr. and to predict the next token which is Mrs., you do not have access to all the future tokens which come after Mrs. And this seems like a trivial point, but that is the whole premise of causal attention. The whole premise of causal attention is that to predict the output, we only have access to the tokens before the output. So we cannot cheat and we cannot look into the future. So the simplest way to explain causal attention is that you cannot cheat. We cannot cheat and we cannot look into the future. The reason I explained the beginning of this lecture with this Harry Potter example is so that you feel interested in this topic and then you don't forget what causal attention is. Essentially, what causal attention is simply is that for every output, the input is only the tokens which come before it. So you check any input and output pair in these four input output pairs which I have. The for every output, the input is only those words or tokens which come before the output. Okay. And now let's start understanding causal attention in a more formal manner, right? So causal attention is also sometimes known as masked attention, and it's a special form of self attention, right? It restricts the model to only consider previous and the current inputs in a sequence when processing in any given token. This is what we saw. To predict any output, it restricts the model to only consider previous and the current inputs in the sequence. This is in contrast to the self attention mechanism, which allows access to the entire input sequence at once. And let us see this in action actually. So if you remember what we did with the queries, keys, and the value vectors, we had an input, and the input had tokens such as, let's say, your journey starts with one step. And here I have shown that every token is a three-dimensional vector. We will multiply this with the trainable query matrix, trainable keys matrix, and trainable values matrix, and ultimately we'll have the queries, the keys, and the values. Now let's see how we compute the attention score, right? The attention score is the multiplication of queries multiplied by the keys transpose. So let's look at this attention scores in more detail. So if I have my queries vector, um, if I have my queries vector to be 6 by 2, and if I have my keys vector to be, let's say, 6 by 2, to get the attention score, what I actually do is I do queries multiplied by keys transpose, right? So it will be a 6 by 2, it will be a 6 by 2 multiplied by, it will be a 2 by 6. So this will ultimately result in a 6 by 6 vector or a 6 by 6 matrix. And the tokens which I'm looking at for now are your journey starts with one step, right? So let's see, your journey starts with one step, and then here my keys are your journey um, starts with one step, right? And basically this 6 by 6 matrix indicates that I have values for every single entry here. So so if I'm looking at journey and that's my query, I'm basically finding the attention scores between journey and all the other words, even before and after journey, right? So this is the attention score between journey and your. This is the attention score between journey and journey. This is the attention score between journey and starts. This is the attention score between journey and with. This is the attention score between journey and one, and this is the attention score between journey and step. Now, this can be represented in a visual manner like this. Your journey starts with one step, and if journey is my query vector, I am essentially finding the attention of journey with all the other tokens, no matter whether the token comes before journey or after journey. Now, pay very careful attention here. If journey is my query, right? So if your and journey are essentially my inputs, to predict the output, journey will not have access to the tokens which come after it at all. So when journey is my query vector, if we are looking at causal attention, ideally we should find the attention scores only between your and journey. All the other tokens which come after this point do not matter too much to us at all, because they are anyway not going to influence the calculation of the next token. Let me explain this point once more. Essentially, what we do in self attention mechanism is that we get these attention scores, right? So for every token, we find its attention with the tokens which come before it and which come after it. But the key point to realize is that for every token, we do not have access to the tokens which come after it at any point in the prediction process. So take a look at the Harry Potter example, right? For every token we don't have access to the words which come after it. We cannot look into the future, and since we cannot look into the future, there is no use finding the attention scores between a token and the tokens which come after that point. So ideally, if you have a 6 by 6 matrix such as this, so let's say this is 1 2 3 4 5 6, 1 2 3 4 5 6, 2 3. So these are three rows, and let me actually copy this and paste it. Let me just do it again here. So these are three rows. This is my fourth row over here, this is my fifth row over here, and this is my sixth row. These are the attention scores, right? This is a 6 by 6. So if we cannot look into the future, for the first token we only need to find the attention score between the first token and itself, so that's this. For the second token journey, we only need to find the attention score between your and journey. For the third token, we only need to find the attention score between your journey starts. For the fourth token, we only need to find the attention scores between your journey starts with. For the fifth token, we need to find the attention between 1 and your journey starts with 1. So all the tokens which come before 1. And for the sixth, we can essentially find all the attention scores between step and all the tokens which come before it. So now if you see all these attention scores which are above the diagonal, which I have marked over here, all of those are not needed at all. All of these attention scores are not needed because we anyway won't look into the future at any time point. Remember, why did we get the attention scores? We got the attention scores between a token and the other token, so that will help us get from the input embedding vector to the context vector. But in self attention, we kind of looked into the future, right? Because for one token, we even found the attention score between that token and tokens which come after that point. And so the value vector which we ultimately so the context vector is a multiplication of the values vector and the attention scores matrix, right? So the context vector for every token essentially had information about the future, and that's not what actually happens when we predict the next token. When we predict the next token, we are not going to have information about the future at all. So ideally, when we get the context vectors, we should prevent access to this future information completely. So all the elements above this diagonal should be essentially set to zero, because we don't have access for one token. We only have access to the tokens before or equal to that current token. This is the main intuition behind causal attention. So this is in contrast to the self attention mechanism, which allows access to the entire input sequence at once. Now, while computing the attention scores, the causal attention mechanism ensures that the model only factors tokens that occur at or before the current token in the sequence. This is what we saw. So, for every token, we should only consider the tokens which occur at that point or the ones which occur before that current token to get the attention scores. To achieve this, for each token process, we mask out the future tokens which come after the current token in the input text. This is the most important sentence. That's why causal attention is also sometimes called as masked attention. So if you look at bidirectional attention, which is self attention, every token essentially attends to all the other tokens, right? So we get information of the attention scores which come before and after a current token. But in unidirectional attention, this is also called autoregressive attention or causal attention or masked attention. There are many names. We essentially mask out all the tokens which come above the diagonal. So essentially, all of these tokens which come above the diagonal, we will set these tokens equal to zero. And that's what this rest of the lecture is going to be about, that how do we exactly set these tokens to be equal to zero. So the rest of the lecture is going to be a bit mathematical, but until now I hope you have understood the intuition of what we are trying to do, right? So we mask out all the elements above the diagonal, and remember that in attention weights matrix, in the attention weight matrix which we had seen before, so here was the attention weight matrix. The main difference between attention scores and attention weights is that each row essentially summed up to 1. So that is a property which we ideally want to retain. So the problem is that if you randomly put all the elements to 0, the rows will no longer sum up to 1. So we'll need to do a normalization step once more so that the attention weights in each row actually sum up to 1. So now let's see how we actually so the task is now we have the attention scores, right? We have to put all the elements above the diagonal in the attention scores to be equal to 0. Let's see how to do that now. So there are actually two strategies to do this, right? And I want you to pause here, and I want you to think, right? The problem at hand is that imagine or take into account this previous lecture. In the previous lecture, we had calculated these attention scores, but now I am telling you that all of these values need to be set to zero. This all of these values which are essentially above the diagonal, these values need to be set to zero. All these values need to be set to zero. So how will you go about essentially calculating the attention's weights? Or another way to think about it is that you have the attention weights, right? What if you set all of these values to zero? Let's say you set all of these values to zero now. What will happen if you just put all of these values to zero? If that is the case, you will see that the rows don't sum up to be equal to 1. So then what you can simply do is that whatever is remaining, so if you set all of these to 0, this matrix will be something like this matrix will be something like point 0.1 0 0 0. It will be point 0.1 0.5 0 0 point oops. So actually The actual values which you need to set to 0 are these ones. Uh, this needs to be set to 0. These three, these two, and this. These values you need to set to 0. So if you set this to 0 directly, what will happen is that this will be point 0.1, 0, 0, 0, 0. This will be point 0.1, point 0.5, 0, 0, 0. This will be 0.05, point 2, point 2, 0, 0, etc. So the remaining two rows also. So now you see the problem here is that each row does not sum up to 1 now. The first row sums up to point 0.1, the second row sums up to point 0.6, etc. So what can you do in this case so that each row sums up to 1? The simplest thing you can do is that the first row, the entire summation is now point 0.1, right? So you divide this by point 0.1. The second row, entire summation is now point 0.6. So you divide each element by point 0.6. 6. The third row, the entire summation is now zero point 0.2 plus zero point 0.2, zero point 0.4 plus 0.05, which is 0.45. So you divide each of these by 0.45. You divide this also by 0.45, and you divide this also by 0.45. What that will ensure is that will ensure that um, each row still sums up to 1. So this is actually the first strategy which is implemented to get the causal attention scores. The first strategy is like you already have the attention scores to which you have applied softmax and you've got the attention weights. You did that in self attention itself. Then what you do is that you just add zeros above the diagonals and you get the masked attention scores. But then you normalize the rows again so that they sum up to 1, and then ultimately you get the masked attention weights. That's the strategy which we saw right now. But do you see the problem with this strategy? The problem with this strategy is that, let's see here again. You see, to go from attention scores to attention weights, we are already doing softmax. So we are doing one step of normalization here. And then again, we are doing one more step of normalization when we divide by the sum of the rows. So we are unnecessarily doing two normalization steps over here. So then the question is, can we do a smarter way of normalization so that we need to only apply softmax once? And it turns out it is possible to do that. And the way to do that is we directly target the attention scores. So let me tell you how we do this. So the way to do that is we directly target the attention scores. Here is where we make our intervention instead of making our intervention in the attention weights. So the way we do this now is that essentially what we do is that all of these values, all of these values which I'm marking right now in circles, which are essentially above the diagonal and which need to be replaced eventually with 0. And what we do with these values is that we will replace these values with negative infinity. We'll replace these values with negative infinity. So let's see what the attention scores matrix now becomes. So the attention scores matrix now becomes zero point 0.6, then negative infinity, negative infinity, negative infinity, and negative infinity. The second row becomes zero point 0.1, uh, zero point 0.1, then 1.8, and then again I will have these three negative infinity values. So I just copy pasted them over here. Then in the third row, I'll have two negative infinity values. So I'll just show this for the three rows. And the third row values will be zero point 0.2. The third row values will be 0.2, 1.1, 1.2. Now, why are we doing this? Because remember that when you apply softmax, what softmax does is that softmax actually takes the exponent. So softmax will, uh, for the first row, each element the softmax will replace with e raised to, so the first element it will replace with e raised to x1 divided by the sum. The second element the softmax will replace with e raised to x2 divided by the sum. So this we are doing for the first row. So let's say, let me mark the first row over here. So if this is my first row, each element will be replaced with, let me mark this again. So if this is my first row, each element will be replaced with this e raised to x1 by some, e raised to x2 by some, etc. Now I want you to check what is e raised to minus infinity. So you'll see that e raised to minus infinity is actually equal to 0, right? So the second element will be replaced with e raised to minus infinity divided by sum, which is anyway 0, because e raised to minus infinity is 0. This third element will be replaced with 0, fourth element will be replaced with 0, and fifth element will be replaced with 0. Essentially, wherever we have minus infinity, all of those will be replaced by 0, because exponent raised to minus infinity is equal to 0 anyways. And the first element will be replaced with e raised to zero point 0.6 divided by e raised to zero point 0.6, so it will be replaced with 1, so it will sum up to 1. Here the first element will be replaced with e raised to zero point 0.1 divided by e raised to zero point 0.1 plus e raised to zero point 0.8. The second element will be replaced with e raised to 1.8 divided by e raised to zero point 0.1 plus e raised to 1.8. So the in each row will sum up to 1, and we'll also make sure that all the elements above the diagonal are essentially 0. So this will make sure that we are not doing two stages of normalization. Here we did two stages of normalization, right? We did softmax followed by every row normalization. But here we are doing only one softmax normalization. That's it. That's this trick of introducing negative infinity above the diagonal. And it's a very powerful trick, and it saves the computations for us. So the more efficient way is essentially you have the attention scores. The more efficient way is that you have these attention scores, and then you apply something which is called as an upper triangular infinity mask. um, what this mask essentially means is that you replace the upper triangular, which is all the elements above the diagonal will be replaced with negative infinity, and then you directly apply softmax only once. So see, here you have only one softmax, whereas here you had one softmax to get the attention weights, and then you had another layer of normalization. So that way there are two normalizations. So this on the other hand is a much more efficient way. We are now just going to see this in code so that you can understand what we are trying to do over here. Remember, in the previous lecture we started out with this inputs embedding matrix, where we had your journey starts with one and step. Okay, so these are the six inputs over here, and there is a vector embedding for each input here, which is a three-dimensional vector embedding. And at the end of the previous lecture we had defined this self attention class. Essentially what this does is that it takes in the inputs, it finds the keys, queries, and the values, it finds the attention scores, then it gets the attention weights, and then it finds the context vector. In causal attention we are going to just make changes in this part so that all the elements above the diagonal are essentially masked out, right? So let's see what is done in a causal attention. So this section is titled Hiding Future Words with Causal Attention. We start with the same inputs, and I'm just printing out the attention weights over here. And I'm first going to show you this first approach. In the first approach, what we do is that we start with the attention weights, which have been already obtained previously. So remember, when we are showing these attention weights, we have already applied softmax before to the attention scores. And in the first method what we do is that we just take elements above the diagonal and put them to be equal to 0. So now here is the mask, which is essentially all the elements above the diagonal are 0, and then we apply this mask to the attention weights. So when we apply this mask to the attention weights, you will see that we have the attention weights matrix, but all the elements above the diagonal are now put to 0. But this presents the problem that every row now does not sum up to 1, right? And that's an issue. So to solve this, what we do is that we simply divide by the summation of the rows. And this is what we saw. This is exactly what we saw actually on the whiteboard over here, if you remember. The first step what we saw over here is you just put the elements above the diagonal to be 0 and then just divide by the sum of the rows. So when you run this will give you the masked attention weights, and this is the main purpose of causal attention. Now I'll show you the second method, which is actually more effective. So here's the attention scores matrix. So remember, in the second method, we don't start with the attention weights like we did in the first method. We start with attention scores. So we start with the attention scores, and then here is the mask which we have. So we have this mask where there are ones above the diagonal, and then we take this mask and use it to replace all the elements above the diagonal with negative infinity. And once we have this, then what we do is that we just have to take the softmax ones. The softmax will make sure that all the negative infinity over here are essentially put to zeros. That's what I'm showing on the screen right now. And softmax will also ensure that the sum of every row is equal to 1. So now if you actually compare these values, so this is 1.5517.4483, and you will see that these are actually exactly the same values, right? The third row is 0.38, 0.3097, 0.3103, 0.38, 0.3097, 0.3103. So essentially both the methods give us the exact same answer, but the second method is actually much more effective because we just start with the attention scores. We replace the elements above the diagonal with negative infinity, and we just take softmax once. We don't have to take the softmax and then again normalize as we did in the earlier method. One more final step before we actually move to coding the um, causal attention mechanism is something called as dropout. So dropout is actually a deep learning technique, and in this technique what's done is that sometimes during training neural networks, we observe that there are some neurons which don't learn anything, and these neurons actually become lazy and they are not contributing anything during the learning process. So let's say if this is my first neuron, this is my second neuron, this is my third neuron, this is my fourth neuron, this is my this is my fourth neuron, this is my fifth neuron, and this is my sixth neuron. Let's say this is my sixth neuron. Now let's say if these six neurons are learning, and we observe that out of these there are two neurons actually which are not doing anything, which means they are lazy neurons, and all the work is being done by these four neurons. One way to solve this problem is that during the training process, what we do is that we make sure that some neurons are randomly turned off. So for example, if during the training process this neuron and this neuron are randomly turned off, and remember these were the neurons which used to do most of the work, but now if these neurons are not there, then these two neurons have no other option but to learn something on their own, right? So dropout actually solves this issue of lazy neurons where some neurons don't do any work at all. The fact that we randomly drop out or we make certain neurons inactive, other neurons have to pick up the pace. It's like working on a group project, right? And if there are, we always have such groups in which there are only two people doing the work and others are not doing anything. But if those two people suddenly fall sick and if they are not available, the others have no option but to work, right? It's the same case with dropout. So what we actually do is that in the case of causal attention, a similar sort of a dropout mechanism is applied where after calculation of the attention weights, let's say we get the attention weights matrix, and of course it will look something like this. All the elements above the diagonal are 0. We randomly mask out certain attention weights, we put them to 0 randomly, and the and this is, what do I mean random is that at every iteration different weights are put to be equal to 0. So the only thing which is fixed is the dropout rate. So if the dropout rate is 50%, it means that in every forward pass through the large language model, 50% of the um, attention 50% of the weights in every row will be randomly put to 0, and the same weights will not be selected each time because the weights are selected in a random manner, but on an average half of the attention weights will be put to 0. That's what's done using the dropout mechanism. So in this figure it actually illustrates that these gray neurons, or rather these gray attention weights over here, are masked out, or they are randomly turned off. And the reason dropout is implemented is that it improves generalization performance. The issue with lazy neurons is that if we are using this neural network on a new problem, then the lazy neurons again won't fire, and so generalization will not be good. So dropout ensures that all neurons are effectively learning something, and we prevent overfitting to noise, or we prevent um, memorization of the data, which usually leads to overfitting and generalization issues. So this is dropout, and let me just show you in code how dropout is implemented now. So let's say if you have a matrix like this, and imagine this is your attention weights matrix for the sake of simplicity. When you have a matrix like this, and when you add a dropout, so torch.nn.dropout of zero point 0.5, it means that on an average, 50% of every row is put to zero. And remember, this is on an average, so it does not definitely mean that half of every row will be put to zero. So you see here, none of these are essentially put to zero, but here you see five of them are put to zero. Here four of them are put to zero. Here three of them are put to zero. So it's a random process, right? But one thing is that in dropout, since we have a factor of zero point 0.5, the values which are not put to zero are effectively scaled by a factor of 2. If we have a factor of zero point 0.4 of dropout, which means 40%, it will be 1 divided by zero point 0.4. So every value will be multiplied by that. So to compensate for the reduction in active elements, the values of the remaining elements in the matrix are scaled by a factor of 1 by zero point 0.5, which is 2. This scaling is crucial to maintain the overall balance of the attention weights, ensuring that the average influence of the attention mechanism remains consistent during the training and the inference phases. So dropout is a very simple mechanism. You can think of attention weights as a light bulbs, right? So if these are the attention weights, think of all of them as light bulbs, and dropout is simply light bulbs going on and off during every iteration, and you can specify the dropout rate. So if the dropout rate is equal to if the dropout rate is equal to 50%, which means that half of the light bulbs in every row will be randomly put to zero. That is what is very important to understand over here. And this prevents overfitting and improves generalization performance. Now that we have learned all of this, we are actually ready to code the causal attention class. We'll start with the same input. So we have six tokens over here. Your journey starts with one step, and you will see that every token is a three-dimensional input embedding vector. In this case, what I'm going to do is that I'm going to create two batches. So this is the first batch. Remember, every batch has six tokens, and every token has three dimensions, right? So when I stack two batches on top of each other, we'll have two, which is the batch size, six, which are the number of rows over here, and three, which are the number of columns. That's essentially the input embedding dimension, right? So this is my input embedding vector. In causal attention, the aim is the same. We will ultimately take in each input embedding vector and convert it into a context vector. But the only thing which changes now is that, let's say we get these attention scores, which are queries multiplied by the keys transpose. The only thing which now changes is that we replace all the elements above the token, above the diagonal, with negative infinity, and then we take the soft max. That's it actually. So the attention weights are calculated like this. This will make sure that all the elements above the diagonal are equal to 0. And then what we do is that we apply the dropout mechanism, which means that in every row of the attention weights are actually plugged off and put to 0 randomly. This improves generalization, as we discussed earlier. And the context vector calculation then stays the same. We just take the attention weights matrix and we multiply it with the values matrix, and we get the context vector matrix. So if you think of the difference between self attention and causal attention, the only difference happens after the attention scores are calculated. After the attention scores are calculated, we replace the elements above the diagonal with negative infinity. We take a softmax and then we apply dropout. So there are two changes actually. The first is the negative infinity and then softmax, and the second change is actually adding the dropout. which randomly puts off some attention weights to 0. You might notice certain things here which I have not explained, such as what is this bias which is equal to false. That essentially means that we are just going to multiply the inputs with the keys, queries, and the values, right? Without any adding any bias term. That's why this bias is equal to false. Then secondly, what is register buffer over here? So why is this mask being created with this self dot register buffer? So the main idea is it's not strictly necessary, but buffers are automatically moved to the appropriate device along with our model, which will be relevant when training the LLM later. This means that we don't need to manually ensure that these tensors are on the same device as our model parameters, which might avoid device mismatch errors. You don't need this right now per se, but if it's there, it's just a better practice. But remember, these three dimensions are the ones which will show up throughout. So b comma number of tokens comma d in. So every input has actually three dimensions which we saw over here: the batch size, the number of tokens, and the input dimensions. That is very important to notice. All right, so now this causal attention class is implemented. So let's just test it out. I am going to assume d in equal to 3 and d out equal to 2. This is the same input output dimensions which we saw in this example. If you see, um, yeah, just take a look at these dimensions over here. Let me scroll over here. Yeah, so the input dimension is equal to 3, which is mentioned over here. The input dimension is equal to 3, but you will see the output dimension is equal to 2. So the queries, keys, and the values trainable weight matrix project every input vector into a two-dimension output space. As I mentioned in the previous lecture, in GPT and in modern LLMs, the input and output dimensions are kept the same. But here, let's just assume this for the sake of this example. So then all we have to do is that we have to define the batch. And here, remember, the batch is 2 comma 6 comma 3. And here, if you see, yeah, so the batch is 2 comma 6 comma 3. That's my input, and then I just define the causal attention. So causal attention class requires actually four inputs. So here I have my d in, I have my d out, I have my context length, and the final is the dropout rate. So remember, context length is batch dot shape 1, the first index. So if you see batch dot shape, it's 2 comma 6 comma 3. So batch dot shape indexed by 1 will be 6. Since I'm looking at 6 elements in the sequence, the context length in this case is equal to 6. Okay. So the context length is equal to 6. What else does the causal attention class need? It needs d in, which is equal to 3. D out is equal to 2. Context length is equal to 6. And it also needs a dropout rate. So here I have just mentioned dropout rate equal to 0. So you can run this and ultimately see this is, yeah. So here the dropout rate is equal to 0. So you have these attention weights before the dropout. Um, and you have actually this, I think I should run this part once more. So this is my causal attention class, D in, D in. Um, Yeah. So now that I print the context vectors, these are the context vectors which I obtain, right? So this is size 6 by 2. This is exactly the size which we saw here. So the context vectors will have a size of 6 by 2, which are 6 rows and 2 columns. But now remember that we have two batches, right? So in the first batch, we have 6 tokens which will be processed, and that will lead to a context vector matrix of 6 by 2. When you have the second batch, that will lead to another context vector matrix of 6 by 2. So that's the second batch. And now when both, remember, we are passing two batches here. So if you see the input, we are stacking two batches here. So there are two batches. So the output will be 2 comma 6 comma 2. So here is 2 comma 6, the first batch output, the first batch context vector matrix, and this is the second batch context vector matrix. So the output size is 2 comma 6 comma 2. So don't be confused that why is the output size or output dimensions not equal to 6 by 2. The reason it's 2 comma 6 comma 2 is that we have two batches and each has a size 6 by 2, right? So this is my context vector matrix and it seems to be correct. Here I have just written another function which prints out the attention weights before dropout and after dropout. So here I have run the causal attention class with the dropout rate equal to zero point 0.5, and I have shown the prints before dropout and after dropout. So you'll see that before dropout, let's say here there were two weights which were active, right? But after dropout, only one of this is active, but this is scaled by a factor of two because dropout rate is now equal to zero point 0.5. Similarly, if you look in the third row, there were three weights which were active before dropout, but after dropout only two are active now. If you look in the fifth row, there were five weights which were active before dropout, and after dropout, none of them are active. Remember, it's a random process. So, on an average, 50% of the weights will be turned off, but it might happen that sometimes all of the weights are turned off. So, you can run this part to check for yourself how the dropout actually works. This brings us to the end of the lecture on causal attention. Remember, causal attention is actually quite simple if you understand the self attention mechanism. The main intuition behind causal attention is that we cannot look into the future. For a given token, we only have access to that token and the information which precedes it. So, what we actually do is that we need to take the attention weights and set all the elements above the diagonal to be equal to 0. And there are two ways of actually doing this. The first way is you start with the attention weights directly, which were computed before from the attention scores and softmax, and you put all the elements to above the diagonal to 0, and then you do the normalization of the rows once more. But here you have to do softmax once, and then you again have to do this normalization of the rows. So that's two times normalization. Instead, we can make this process a lot more efficient by just starting from the attention scores matrix before we applied the softmax, and then put all the elements above the diagonal to be equal to negative infinity. And then when you calculate the softmax, it will automatically ensure that all the elements with negative infinity are set to 0, and every row essentially sums up to 1. So that's how you get the attention weights, and that's how you make their elements above the diagonal to be equal to 0. But in causal attention, we don't stop there. We usually even add dropout. So certain weights are randomly masked out and set to 0 to improve the generalization performance, and different weights are selected in every forward pass. So this makes sure that there are no lazy weights, and every weight essentially is learning something during the training process. And then we implemented a causal attention class which actually looks like this. If you see, it's like 15 to 20 lines of code, and I hope you have understood every single aspect of this code over here. Remember these three dimensions of the input shape, which is the batch size, the number of tokens, and the input dimensions. As you must have noticed in every lecture, I pay a lot of attention to dimensions because ultimately I think that understanding attention really comes down to matrices, and people are not really comfortable with matrices because they cannot visualize the dimensions. That's why I pay a lot of attention to dimensions. In the next class, what we'll be doing is that we'll be advancing further. Until now, we have finished looking at self attention, we have finished looking at causal attention. In the next class, we'll start looking at multi head attention. Then we will be completely ready to understand key value cache, and finally, we'll be fully ready to understand the multi head latent attention. As I mentioned, always try to make notes as I'm explaining so that you fully understand what's happening in the lecture. If you just listen to the lecture, you will feel as if you're understanding, but the concepts will not be strengthened. So the lectures are going to get deeper and deeper now as we proceed into the further modules, and I really want you to stick with me through this course and finish all the lectures. So stay motivated, keep making notes and ask doubts, so we'll be able to clarify them. Thanks a lot everyone, and I look forward to seeing you in the next lecture.